Okay, now we're moving on to rational functions. We're going to start by looking at asymptotes. So you would have looked at these a little bit in grade 11. So rational function is a function which takes the form n of x over d of x, where n of x is the numerator and d of x is the denominator. And they are both polynomial functions where the degree cannot be 0. Sorry, where the denominator cannot be 0. The degree of the denominator needs to be greater than 0, or the function f of x is simply a polynomial function. So examples are listed there. Those are all rational functions. So rational functions have discontinuities because they have variables in the denominators. So it all comes from the golden rule of math that we cannot divide by 0. So that is always what causes these discontinuities in these graphs. Since rational functions are expressed as fractions, the denominator cannot equal 0. The denominator of a rational function can be made equal to 0 for a particular value of the independent variable. Then this value of the variable is called a non-permissible value of the function. In the examples above, the non-permissible values are 1, positive and negative 3, and negative 2, respectively. Note that not all rational functions have non-permissible values. So for example, f of x is 1 over x squared plus 1. There's no value that makes the denominator equal 0, so there's no discontinuities in that graph. So if a rational function has non-permissible values, then the graph of the rational function will not be a continuous curve. There must be some kind of discontinuity in the graph. So here there are two types we're going to learn about this year. Infinite discontinuity, which is a vertical asymptote on the graph, or a point of discontinuity, which is a hole in the graph. So in this lesson we will examine the behavior of rational functions with infinite discontinuities. So graphing a rational function using a table of values. So consider the function 1 over x minus 1. Since division by 0 is not defined, the non-permissible value for this function is 1. Whoops, I haven't selected my pen. So it is 1. Complete the table of values below. Plot the points on the grid, but do not connect. So if I complete this table of values, I have negative 1/6, negative 1/3, negative 1/2, negative 1, not defined at 1, and then 1, 1/2, 1/3, 1/6. So you notice that these are symmetrical. Sorry, it's not quite symmetrical because that should be 1/4. We skipped some values here. So it starts out a little bit symmetrical, but then it does change a little bit. So we could plot these points. I'll let you do that on your own time. You can all plot those points. To investigate the behavior of the rational function near the non-permissible value, we need to include values of the independent variable closer to the non-permissible value. So if we look at 0.5, that gives us the value of negative 2. If we look at 0.9, which is even closer to that value of 1, we have negative 10. 0.99 gives us the value negative 100. We know it's not defined at 1. What if we go on the other side of 1? Slightly larger than 1, we have the value of 100. 1.1 gives us the value of 10, and then the value of 2. Well, now if we look at our calculator, we see that we get a graph that looks like this. And this would include those points that you should have plotted a minute ago. So describe what happens to the value of the function, so that's describe what happens to the y values, as x get more and more positive. In other words, as x approaches infinity, what happens here? So as x is getting larger and larger and larger, it looks like this graph is approaching the x-axis. So that means it gets closer to y equals 0. Describe what happens to the value of the function as x gets more and more negative. So now if we look at going past negative 5 and continue, it also looks like it gets closer to 0. Oops, closer to. From the options in the curly brackets, circle the correct alternative in each of the statements below. As x gets closer and closer to the non-permissible value of 1 from the left, the value of the function approaches positive or negative infinity. So as we're approaching 1, sorry, I drew this wrong. This needs to be over here. So as it's approaching 1, our values are getting smaller and smaller very fast from the left. So it's approaching negative infinity. From the right, it's approaching infinity. So asymptotes. A line that a curve approaches more and more closely is called an asymptote. With reference to the exploration on the previous page, as x gets closer and closer to 1, the graph of f of x gets closer and closer to the line with the equation x equals 1, but will never reach the line x equals 1. The graph has an infinite discontinuity at x equals 1, and the line called x equals 1 is called a vertical asymptote of the graph. As the absolute value of x increases in value, the graph of f of x gets closer to the x-axis, which is the horizontal line y equals 0, but will never reach it. The line y equals 0 is a horizontal asymptote of this graph. So note that a horizontal asymptote is not representative of an infinite discontinuity, but it is still an asymptote. Vertical and horizontal asymptotes are often represented on graphs with dashed lines, but these dashed lines do not form part of the graph. So these are like invisible lines that sometimes we sketch in, we like to give the equations of, but they are not part of the graphs. Another thing to remember is that it is possible for a graph to touch or cross the asymptote. It's that it'll never overlap the asymptote. So it'll never be the asymptote, but it can cross it. So we will see kinds like this, where you have an asymptote here, where you have two asymptotes, two vertical asymptotes, you have something, oh, what happened? You have a section of your graph here, then you have a section of your graph here, and you have a section of your graph here. So this is a horizontal asymptote. The middle section does cross it, but what an asymptote says is that this line and this arm will never be that line. It'll never overlap completely. It's going to get infinitely closer to it, but it'll never completely overlap. Okay, we're going to kind of skip the rest of the investigations. Again, if you want to play with these a bit, you can see what the investigations are doing. We are going to skip to the summary here that tells us how can we find these asymptotes. So we have two kinds of asymptotes, vertical asymptotes and horizontal asymptotes, and we have rules. These are very important rules. You always should start by realizing that in order for these rules to apply, the numerator and denominator need to have no factors in common. So you've already factored the top and bottom of your rational expression. You have canceled out any factors that are the same on the top and the bottom. Now we're ready to look for asymptotes. So vertical asymptotes, algebraically, we can find the equation of vertical asymptotes of rational functions by finding the zeros of the denominator. The equations will be x equals the zero values of the denominator. So those ones are quite simple. It's these ones that take a little bit more memorization. The graph of f of x has a horizontal asymptote under the following conditions. If the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is a horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then the line y equals a over b is a horizontal asymptote, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. So let's look at this example. Algebraically determine the equations of the asymptotes. First thing we always need to do is factor. So x squared plus x minus 6. That's an easy one to factor. 2x squared minus x minus 3 is trickier. So we're still looking for two numbers here that multiply to negative 6 and add to negative 1. But now we're going to use those to split up the middle term. So now I'm going to factor by grouping. So what's common here? 2x squared minus 3x. The only thing common there is 1. is 1x. Sorry, here 2x and 3, the only thing common there is 1. So this factors into 2x minus 3 times x plus 1. So at this point, we want to check if we have any factors in common from the top to the bottom, which we don't, which means we're ready to apply these rules. So the vertical asymptotes are easy. The zeros of the denominator. So there's 1 at positive 3/2. And there is 1 at x equals negative 1. Those are the equations of the vertical asymptotes. They match your non-permissible values. The difference is when we're writing non-permissible values, we write x cannot equal negative 1 and 3/2. When we're asked for the equations of the asymptote, then we write x equals 3/2 and x equals negative 1. What about the horizontal asymptote? So we know for our horizontal asymptotes, we need to compare the degree of the top and the bottom. The degree of the numerator here is 2 because it's x squared. Same for the degree of the denominator. So their degrees are equal. So if we go back up to our rules here, it tells us if the degrees are equal, we divide the leading coefficients. So the leading coefficient of the numerator was 1. The leading coefficient of the denominator is 2. So therefore our equation is y equals 1/2.